Hey kids, ready for another day of accumulation functions. Remember, our big idea is that we have an accumulation function. You have some function, in this case, our function is h, and it has an integral in it. And it has an integral from some starting value, and our starting value is 1, and stops of x, stops at varying values, and the very function that we are collecting values under is itself the graph of the derivative, not the accumulator function. So the graph I'm looking at here, whoa, I missed. F by the first fundamental theorem is the derivative of the accumulator function, right? H prime is little f, the graph I'm looking at. So these values, there start to be a rhythm to these problems, right? So the first thing they're asking us to do is just calculate, plug and chug. What is h of 1? Well, h of 1 is going from the starting value of 1, collecting values under f of t. You're kind of used to that now too, right? What's that situation if you're going from 1 and not stopping anywhere? Right? My pen is frozen for a second. So 1 to 1 under the graph of f is going to be 0, right? So the graph I can't see, I have 1 point on it because I started at 1 and they told me to stop at 1. Don't forget endpoints are included here. They're telling me to use the accumulation function from 1 to 7. Now it says find h prime. Well, h prime by the first fundamental theorem is the same thing as little f at 4. So now you were just reading from this graph. What is little f at 4? Well, that's 2. Remember, what this is a slope on the graph of g at 4. And I don't see the graph of g. On what interval or intervals is the graph I don't see concave up? Concave up goes with h double prime being positive. And they want me to justify my answer. So here's what they want to see out of that. Where is h concave up? The answer to C is since right, the second derivative of h, well, I guess I should even write it like this, right? If I want to fully justify, right, start from the beginning, right? H prime is equal to f. Therefore, h double prime is equal to h prime. F prime, excuse me. That's my justification. You can write it fancier than that, but you don't have to. Also, in any one of these problems, if you have stated the fundamental theorem once, right, you don't have to keep stating it, but you need to justify each separate thing. I hadn't talked about the first fundamental theorem yet, so I hadn't had to justify anything. So I said, first fundamental theorem, h prime is equal to f, which means h double prime is equal to h prime. Therefore, when f prime is increasing, h is concave up. So where am I increasing? Where is the graph of the derivative increasing? From 1 to 3 and from 6 to 7. And remember, AP doesn't care if you put closed brackets or soft brackets on interior points. Close off your endpoints, and of course, never put a closed bracket or an equal sign on infinity. Now look at D. Find the value, think height, value of x, where h has its minimum. That's the height on the closed interval 1 to 7. So a minimum, its minimum means absolute minimum. So I'm going to go up here and answer D. Suspects for absolute min. Endpoints. And anywhere the derivative does not exist, look at that blue graph, it exists everywhere on 1 to 7. And where the derivative changes from negative to positive. This derivative only changes from positive to negative. So therefore, this is a maximum, so it is not on my list of suspects for the absolute minimum. So my only candidates are 1 and 7. Look at part A. H of 1 is 0. Now, I don't know what h of 7 is, but I can talk about its value relative to 0, can't you? I don't know what it is, but if I'm starting here, the integral values I'm collecting and accumulating are all positive. So you are summing all of these positive integral values, and then you are going to sum these negative values, and you are going to then sum all the positives and all those negatives together. But given the amount of positives and the amount of negatives, what is h of 7 going to be, positive or negative? It's certainly not going to be 0, is it? H of 7 is positive. Therefore, h of 1, which equals 0, is the absolute minimum. Okay? All right, now in this video, we are, since I went through every single example in the last video, I have 2 more examples to do with you. 3 more. I am not going to do them all. I want you to try them on your own. And in our live session, we're going to talk about the rubrics that go with these next ones, because these next ones are all from a previous AP. Look at that, 1999. How old were you then? So I'm not going to go through each one of these, but I'm going to highlight and talk about a couple of important pieces. I picked out each one of these examples because there's a twist in each one of them. So I don't think you're going to have a problem with this. Straight up calculate, right? But look at this language. I think it's only the language that would throw you on this one. So I don't want this to be a dagger for you. Remember, you still have our big idea. G is the accumulation function. That's the accumulator function. By the first fundamental theorem then, G prime is equal to the graph of f, the integrand. That's the big idea. So plugging and chugging is not going to be a big deal. Find the instantaneous. What does that mean? Instantaneous. What is that? Derivative, right? So what is this actually asking you? What is the derivative at what number? Well, we've done this before, since by the first fundamental theorem, G prime is what? So you're just reading. So I don't think that problem, you've seen that problem before, you just haven't seen it written in words. We just did a problem like this. Find the absolute minimum value. So they actually want a height on the closed interval. Justify your answer. So what I'm going to say here, the hints that I'm going to give you here, are your suspects. Make a suspect list and include the endpoints. And where the derivative, what are you looking for? A minimum. So where the derivative changes from negative to positive. Okay? And then don't forget to justify which one of those, right? You have two endpoints. So you've got x equals -2, x equals 4 are your two endpoints. And then just like the problem before, you don't have any interior candidates, do you? Because the derivative only changes from positive to negative in the interior, which is a maximum, and they asked you to look for a minimum. Now the trap is a trap. The trap in this problem, which is not referring to the trapezoidal rule, is that students will say, oh, the derivative does not exist at 1 or at 2. That is not true, right? And what I mean is the derivative of g prime is f, and f exists everywhere on this interval. The second derivative of g does not exist at 1 and 2, right? The graph you're looking at is the graph of f. The derivative of the accumulator function. You are right that there is a corner at 1 and a corner at 2. And corners mean derivatives don't exist, but it means the derivative of the blue graph does not exist. Remember, g is the accumulator function. You don't see that graph. That graph does have a derivative everywhere because its derivative graph exists everywhere on the interval -2 to 4. So with that idea, look at how they state 5D. The second derivative of g is not defined at 1 and 2. We knew that. Duh. The second derivative of g. How many of these values are x coordinates of poi on g? Justify. So here's what they're trying to get you to realize, right? It is the second derivative that tells me about a change in concavity. But you need to look at the first derivative and know that concavity, point of inflection, is where the second derivative changes sign, but that's also where the first derivative changes direction. Which one of those places where the second derivative does not exist or the first derivative changes direction happens? Is that 1 or 2 or both? Right? X equals 2 is a corner. It is where the second derivative does not exist, but the second derivative would not change sign because the first derivative did not change direction. And that's what they're looking for in the justification. Okay, so again, I'm not going to go all the way through this one. I just wanted to highlight these pieces for you to try. And then when we're together, we're going to look at the rubric and what exactly AP puts out that they want to see. This one is even earlier, 1997, OMG. Look again, look at the corners. There is a non-differentiability issue here and a non-differentiability issue here. But that is not a non-differentiability issue on G. Once again, G is the accumulator. It's the graph I don't see. By the first fundamental theorem, G prime is the graph I'm looking at, the integrand. Notice the graph of the integrand is a semicircle and 2 line segments. You won't have a problem with that. You won't have a problem with this, but let me save you some time. They wrote the words open and they used the symbols open. You don't have endpoints as suspects. They're asking you not to consider endpoints. So for your suspect list, you only have on the interior of the graph where the derivative, and I'm looking for a maximum where the derivative changes from positive to negative. Your only suspect is 2. And they're going to want you to justify that. Notice they don't need a height. They only asked you for any value of x. And you did not have to consider the endpoints because they wrote open interval and they used notation for open interval. But I did want to, this is kind of a new one. Write an equation for the line tangent to. Stop reading. Stop reading for a minute. Right after they say write an equation for a line tangent, do this. Right? Now, keep reading. Find an equation for the line and the tangent up to the graph at x equals 3. Okay, so put the 3 there. Look at part A. Hello. That often happens. Your answer from part A is going to go here. But what's this? That's the slope, isn't it? Where do you get the slope? You need g prime at 3. But what is g prime equal to? F. Oh, look at the graph. G, the one point they labeled, was when x is equal to 3. Kind of cool, right? D, we talked about, find the x coordinate of each point of inflection. Justify. Point of inflection is where the second derivative changes sign. But that is also, and you don't have to write that, where the first derivative changes direction. Right? So, and again, open interval, well, that's more obvious because you can't have a change of concavity and endpoint. So look at the graph of f. It changes direction here, and it changes direction here. Right? So both, even though this is a point of differentiability, this is a point of non-differentiability, but that's okay. It's where the second derivative changes sign, right? Or g prime changes direction. G prime, which is equal to f, and that's what you would say to justify your answer. G prime is equal to f, therefore, you have a point of inflection everywhere the first derivative changes direction. That would be at x equals 0 and x equals 3, and they did just ask you for an x coordinate. This one is a little bit more recent, and there was a twist to this problem that we hadn't seen before this year. Look at my accumulation function. My accumulation function is still called g. So by the first fundamental theorem, g prime is equal to the graph I'm looking at, which is the graph of f. They are telling me that I am looking between -4 and 3, including the endpoints. They're also telling me I have 2 quarter circles and 1 line segment. But look at that accumulator function. It's not just an accumulator. So wait a second. If g of x is not just an accumulator, it's an accumulator and 2x, g prime isn't just f, right? Right? Can you see where I'm going with this? Let me write it out. G of x is equal to 2x plus an accumulator. G prime of x, well, if g of x is a sum, the derivative of a sum is the what? Sum of the derivatives. What is the derivative of 2x then? Right? And what's the derivative of an antiderivative? Whoa. Right? So that, we hadn't seen that before. We had seen constants here. So if that was just a 2, it wouldn't matter, right? Because g prime would still be the derivative of a sum is the sum of the derivatives. But if this thing here was a constant, the derivative would just be 0. So you're left with the derivative just being the integrand. But this time it is the integrand plus 2. So be careful when you calculate -3, right? What is g of -3? G of -3 is 2 times -3 plus the accumulation of 0 to -3. Oh, snap. So I have to start at 0 and go back to 1 to -3. Negatize because you're going backwards. So this is going to be a negative value. And then you have -6. Be careful. How about g prime of x? Done. Right? Evaluate g prime of -3. Well, what is g prime of -3? That is 2 plus f of -3. What is f of -3 though? 0, right? Crazy. So look at the next one. When it says determine the x-coordinate of the point at the point at which g has an absolute maximum on the interval that includes the endpoints, justify your answer. So for part B here, my suspects are the endpoints. I forgot what it was, 3. And where the derivative changes from positive to negative. But that's around where the derivative is equal to 0. Be careful. Where is g prime of x equal to 0? Oh, snap. G prime, it's not just this graph. This is the graph of f. Remember, g prime was 2 plus f is equal to 0. So that is actually when f is equal to -2. Oh, this was a twisty, tricky problem. So I had to get that out of my way. Find all values of x on the open interval. Look at 1c. One C, open interval, right? Because they're asking for points of inflection, so I don't need to consider any endpoints. Give a reason for your answer. I think you're okay with that one. Look at D. Find the average rate of change on a closed interval. Then it says there is no point C on the closed interval -3, -4 to 3, for which F prime is equal to that average rate of change. Explain. So I'm going to erase this stuff up here so we can talk about this problem, because this is part D. First says find the average rate of change of F. That is not my accumulator function. That's the average rate of change of the graph I'm looking at. The average rate of change is the slope of a secant. The slope of the secant is little f right? And they've given me values to look at. So the average rate of change of the graph I'm looking at is -3 minus -1 over 7. -2/7 is the average rate of change of little f. So check, done that part. Now it says there is no point in the domain of -4 to 3 for which little f prime is equal to that. Now remember, the average rate of change is the slope of the secant. Here it is. There's the slope of the secant. There is no derivative on this graph that is equal, right? I can't draw a parallel secant line to that. Why? Explain why this statement does not contradict the mean value theorem. The mean value theorem guarantees a slope of the tangent, right? The slope of the tangent will equal the slope of the secant if, remember I told you they were going to test you on the conditions of the mean value theorem. If what? F was continuous on the closed, and it is, but F had to be differentiable on the open. Is it differentiable on the open? Therefore, does not contradict the mean value theorem. Cool. Notice that on that problem, there wasn't a whole lot of actual calculation and math to do, right? The most difficult thing I did was calculate the slope of a line from Algebra 1. But my interpretation of what was going on is what was going to get me the points. So again, we will, in our live session, we will talk about I will show you the AP grading rubrics for all three of those problems, the 2011, 1997, and 1999, so that you know exactly what, you don't want to write too much, you don't want to write too little, and you want to write what you're going to get the most points. Each one of these problems on the true AP exam is worth 9 points. Okay? And on these problems, you want to try to get 9 out of 9, because you're not going to get 9 out of 9 on them all. All right, I will see you in our next live session.